Hello, welcome back to the video series for Geography 300, Geographical Data Analysis at WVU. This section of the course is going through point pattern analysis, and we've now seen in the previous two videos approaches to point pattern analysis using density-based approaches and distance-based approaches, both of which go off of the two assumptions of complete spatial randomness. That points are equally likely anywhere, looking at density-based approaches, that points are truly independent of each other, looking at distance-based approaches. Now, we can then say there are some critiques of these techniques. That's what this video is looking at. The first criticism or critique is simply that most of the time if we're studying something within geography, the idea of complete spatial randomness is that basically there's no geographic processes affecting those points. But if it's worth studying, that seems like a really silly null hypothesis. There's no way we would expect that to be true. Using the H0 or H0 to stand in for null hypothesis. Complete spatial randomness is just almost like a really silly example here. Why would we even test against something that we would consider so geographically unlikely? There are, as I kind of alluded to with the quadrats, and we can do something similar in how we set up these simulations for the Monte Carlo testing of Ripley's K. There are ways to sort of address this, but they're again very challenging to put in practice. So I can have more complex ways of generating those predicted values of how many cells I expect to have no points, 1 point, 2 points, 3 points, and so on. Or I can have more complex ways than just complete spatial randomness of generating my Ripley's K Monte Carlo simulations. Those, as I said, are often quite challenging to put into practice. So we're not doing them for this class, but be aware that that is at least a theoretical way of addressing this criticism of why would we ever think complete spatial randomness is a geographically plausible situation to even be in the first place. The second criticism in a way, it's related to that first one. Really going in on that complete spatial randomness assumption of independence. That in pretty much any point pattern worth studying for geography, there's very likely to be dependence somehow or other. But I'm pulling that out to really hone in and illustrate why this first assumption, this first critique, is a valid criticism. There's no reason we would expect crime patterns to be independent of each other, especially if any of those are repeats of the same criminal. There's no reason to expect complete spatial randomness and independence of the location of tree species, because most of the ways trees would reproduce, through seedlings and so on, is going to involve some kind of dependence of the parent with respect to the child tree. Again, with more complex math, we can try to address those through our predictions for Ripley's K and for the quadrats with chi-squared. The third critique doesn't necessarily have a really clear resolution like these first two did. But we are assuming the density of points, or the number of points, is as given. We are not questioning, okay, there were 28 trees in the study area, or 57 tornadoes, or 38 burglaries. We are just flat out assuming that 20, 23, 57, 38, whatever, we are assuming those numbers are immutable. We're not considering the possibility that there could have been more trees, or fewer trees, or more burglaries, or fewer burglaries, or more tornadoes, or less tornadoes. We are using that value, lambda, for the density as part of our calculations. The possibility of having a different number of points, as opposed to just rearranging the points we have, that possibility of a totally different number of points, not considered at all. And kind of difficult to consider at that point. So that's a critique, not really any good way around it. The last critique is one we've seen before, equifinality. That we may be told your points are clustered, but we don't know why. It could even be going back to the initial example I gave. It could be going back to our trees are clustered in one corner of the study area. We don't know if they are clustered because the first assumption of complete spatial randomness is broken, and there is a particular soil type there, or a stream that they're congregating around. We don't know if that's why the points are there. We don't know if instead it is something breaking the second assumption, a complete spatial randomness. That happens to be where the parent tree got established. The seeds do not fall very far, and so the children are near that parent. We cannot tell the difference between breaking the first assumption and breaking the second assumption with a single point pattern. We might be able to look into the biology behind how those trees propagate and what leads them to thrive, and have a better understanding of what's going on. From the pattern alone, we cannot tell the difference. That's why equifinality comes into play here. And so we have these four different critiques. Complete spatial randomness is kind of a strange thing to even be considering as a null hypothesis within geography, because we so assume, we so expect it to not be true, especially with the case of independence between the different points. We are not considering the possibility of a different number of points, and our results in terms of being able to use these results to come up with some kind of policy or anything else is held back by equifinality in being able to really guide how we use these results going forward. So those are the 4 critiques. The next video and final one is looking at how we write up and how we present the results of a point pattern analysis study or set of studies. So again, thank you for watching. I will see you at the next video.